Absolutely. So yes, as was mentioned, my name is Bryant Hagen. I work for White Hat Security. I'm originally from Wisconsin. I got my degree in information assurance and cybersecurity at University of Wisconsin Stout. One of my professors worked for the NSA, and he introduced me to cryptography, cryptanalysis, and cryptology. And it kind of struck a nerve with me, and I got really attached to it. And so I started reading up and studying and learning about the history of cryptography. And one of the reasons for this talk is it's a part of a series that I usually present. The first one being Cryptography 101, History and the Basics. Second one being Cryptography or Cryptology 102. That is the study of making codes. And then Cryptanalysis 103, which is the study of breaking said codes. The cryptology and cryptanalysis ones, those run a little bit more in depth. So if you have the basic understanding, you'll be able to understand how the attacks work and how the creation of the what the idea is behind creating these codes. So, what is cryptography? Well, cryptography in a nutshell is the study of making and breaking secret codes and/or ciphers. This has been around pretty much since math was invented. Once math was invented, they realized that we can use math with words and phrases and letters to change the meaning. It's broken up into two basic classes, the first being cryptology. Cryptology is the study of making the secret codes and ciphers, whereas cryptanalysis is the study of breaking those secret codes and ciphers. You need to understand one in order to do the other. So if you have an understanding of cryptology, then you can understand how the cryptanalysts are attacking your codes. Or if you can understand cryptanalysis, you can understand why it's so frustrating when you're trying to break a code, and you'll be able to understand cryptology a lot more in depth. So in the broad spectrum, where can cryptography be applied? The short answer is everywhere. It's essentially allows you to secure data at any level and allow you to essentially protect all aspects of your information, be it in transit or on a database somewhere. The second question being, where should it be applied? Can anybody guess where should it be applied? Everywhere you can. That's the answer that I'm going with. Yeah, exactly. So pretty much you want to go with everywhere you can. The reason you want to go with everywhere you can is so that if one aspect gets compromised, then the data is still secured for an amount of time, like i.e. a database. If somebody gets into the database, but you encrypt your passwords, it's like, yeah, they got into the database, but we encrypt our passwords. We just tell you to change your password, and then that data becomes completely useless. That's kind of the idea. So when I worked within source code analysis, we treated the application, so the application being like a web application or a mobile application. The web application and mobile application is like an island. You can trust anything that the application sends within itself. However, if you're pulling data from user input or you're pulling data from a database, that it becomes untrusted data because of SQL injection and cross-site scripting. Even then, and even the own file server can cause some problems if you are worried about internal threats. So if you treat it like an island, it's pretty. You want to keep it singular to itself. So going over the basics of cryptography, we have all sorts of algorithms out there: AES, DES, different hashing algorithms, RSA, but all of them have a few key features. The first is the message. This is what you want to protect. This is the thing you want to encrypt. This is the thing that you want to hash, et cetera. It's all the way down the line. You essentially want to keep, this is the data that you want to keep secret from somebody else. The second aspect of it is the encrypted information. This is post-encryption. This is the ciphertext. This is what you're going to be sending, or this is what you're going to be storing. This is the end product for encryption as a whole. And then finally, the key and the inverse key. You can, unless it's a one-time pad or something like that, even if it is a one-time pad, you can still understand and give it away as the inverse key to the encrypted message. By the way, if anybody has any questions at any point in time, please feel free to stop me. There will also be time for questions at the very, very end, so if you want to wait until the very end, please feel free to either stop me, raise your hand, just let me know that you would like to ask a question before we get way, way deep. So starting we're going to start way, way back. A few of you may be familiar with the Caesar cipher. This is the like Boy Scout decoder ring kind of cipher. Well, it started off as an actual cipher that Julius Caesar would give to his commanders, and they would pass secret information. So the cipher works, if you're not familiar with it at all, the cipher works by shifting all characters by the same number of spaces to the right. The right being A to B, B to C, so on forth down the line, with Z wrapping back around to A. This is what's known as the key, the number of spaces it shifts. So a shift of 1 would be A goes to B, a shift of 2, A to C, and so on forth down the line. So if the plain text being hi LASCON and the key is equal to 3, you end up with jargon. So there are only 25 possible keys because the second that because of what's known as modulus, it is a modulus of 26. Whereas if you shift A 26 spaces to the right, you wind up with A. Not really that great of a cipher if you shift everything by the equal amount. It still is useful. It's especially when you have a time limit. So if the data is only good for a set amount of time, you'll be okay. So like this next line, this data is only good for about 30 seconds. However, if somebody has a phone or a laptop that wants to try it out, I'll leave it up for about 10, 15 more seconds, and you can feel free to try to break it if you would like. However, once that time limit is up, you get the answer. Next slide is Visionaire. So it's pretty much, it still has its uses. You can pass notes in class or whatever, or around the office, and nobody will understand it. So if you have like a distinct time limit on your codes, it still is useful, even though it's very easy to brute force with a couple hundred, with some time, or a couple hundred people.
You mean by limited time, the ciphertext itself is going to go away.
Yeah, exactly. So So this is an example of if somebody was able to intercept this text, this is an example of something being very easily brute forced. Because if a commander received this information, but he didn't have the key but intercept a messenger, all he would need is a couple of scholars who odds are they were right next to him who were decrypting their own codes, and he would say, decrypt this, and then he'd be like, you get 1, you get 2, you get 3, you get 4, you get 5, etc. And with enough manpower, you can brute force this within a reasonable amount of time. It takes maybe a couple of hours with enough people, and at that point, you understand and you're able to react. So we're going to jump forward to Visionaire, but this is this is an example of just a brute force attack way back in the day. So what the French did, they studied this type of cipher, and then they said, this was in about 1200, give or take, and they said, and they've been fighting the English, and they said, why can't we expand on this? So Vigenère is actually an expansion of the Caesar cipher. So the Vigenère cipher was created by the French when facing the English, and this was a perfect example of a code that at the time was incredibly powerful, and it required a crazy amount of crypto-analytical knowledge in order to break it. So what it does is it takes the Caesar cipher method, but it applies it to a keyword. So the keyword test would shift the first letter 19, the second letter 4, the second letter 18, or the third letter 18, and the fourth letter 19. So what it would do is it would apply the Caesar cipher shift method across each letter that goes down the line. So if we were to take high LASCON again, you can see that T to H, E to I, S to L, T to A, and then so on and so forth. You just repeat the keyword down the line.
So each letter has a different shift.
Yes, and then what you would do is if you knew the keyword, you would just shift it back. So it was incredibly easy to encrypt and decrypt messages if you had the keyword. But if you didn't have the keyword, good luck brute forcing that, because you'd have to basically try every single shift across every single letter, and that's just not feasible. Plus, you would get you have the potential to get a completely different message. And then so what you would do is after that you would wind up with a completely different ciphertext. And then, yes, reversing the process is the same as using the Caesar cipher. You would shift it back per each letter. So the British, you can solve this problem using a computer. It would take some time, but you could do it. But the British, only a couple of years after this was created, were able to break it. They didn't have any rainbow tables or powerful computers or an understanding. So how did they do it? That's the real question. The answer is not all letters are created equal. Look at the English language itself. E's are abundant, like I's, O's, U's, A's, etc. So they used that against itself. So the longer the text, the easier it is to find the patterns. So what you would do is you'd start looking for patterns of letters. For the very short message that we had, it's closer to a one-time pad, which is very difficult to break. This is very difficult to crack. However, if you have a longer text, you start seeing patterns. And patterns kill encryption. This has been the case for now thousands of years. So what they did was they used what's known as displacement and coincidence. So what displacement and coincidence means is that they would displace the first letter by 1 and then see how many matches they had down the line. So in this case, there's no matches up until you hit G. So these two G's would match up. That is what's known as a coincidence. So for longer texts, you would see like you'd see one or two coincidences, and then when you would reach the length of the keyword, so in this case 4, it would shoot up to like 20 coincidences because you're shifting the letters by the same amount. So the idea behind that is is you would shift a letter 18, and then you'd go advance forward, shift another letter 18, shift another letter 18, shift another letter 18. And the odds of you hitting the same letter over and over again increase exponentially. So what happens is, that way you'll be able to find the key size. You'll be able to see exactly how long the key is and what you're working with. This is significantly more prevalent in longer messages. So the short message that I have here, it would be really difficult. It's really difficult to do. But the longer the message, the easier it would be to find. And then what you would do is, with that key length, you would then go back and then try to find percentages of letters. So you have your percentage letter uses. So here's a table of percentages. So you have E being 0.127 out of a couple hundred characters, and so on down the line. So you would start and see, okay, what's my most common letter that I have? Let's replace that with E. Let's replace every instance of that with E. And then you would go down the list and see, does that make sense? If it doesn't make sense, it's like, okay, let's try the next one. Let's try the next one. And you would just basically kind of replace bits and pieces of it, or excuse me, I'm sorry, I'm stepping ahead of myself here. So you would go each space within the key, and then you would say, okay, let's shift it by 1, let's shift it by 2, let's shift it by 3, and then you'd go to the next one, and then you'd figure out exactly how frequently these characters would show up, and then you'd start looking and say, okay, well, this is definitely an E, this is definitely a Q, this is definitely an R. And eventually you would find that you're starting to piece together most of the plain text. And you would just be able to fill in the blanks once you start reaching these, uncommon letters like Z, X, Q, and W, and V. So, but at that point, you've already broken it. All you need to do is just find the major chunks and where they are. And once you find the major chunks, you'd be able to break down the ciphertext back into its plain text form, and you wouldn't even have the key or the plain text. It was very time-consuming to do, but it was their way of breaking it without having to resort to just, I guess we have to brute force it. I guess we have to just keep going. So this was around in the 1200s. The next cipher is something that all of us are probably really familiar with. How many of you have seen The Imitation Game? Wonderful. So the next cipher is the Enigma cipher. And this one has been very interesting to study for me because it is so complicated. So here's what happens. I press a letter, A in this instance. It gets sent into the plug board. Here's what the plug board looks like. So if I press letter A gets sent to some other letter like O, and then it goes into the rotors. So A goes to O, it goes into the right rotor, into the middle rotor, into the left rotor, all the while being jumped around because they have their own, within the rotors, they have their own links and changes. Loops back around the reflector, gets bounced around, and then out the right rotor, highlights the letter G. And then when I press that key, it advances the rotor, the first rotor, the rightmost rotor. So when I press A again, it goes back to O, but then it takes a different path all the way around and then goes to C. So I can sit there and press A 26 times and potentially get 24, 25 different answers. It was very sophisticated. It was very unique. And the problem was there were just so many ways that because when the Allies were able to capture an Enigma machine, they had the rotor positions. But the problem was they didn't have the plug board. The plug board was able to change every single day. So what you would do is you'd plug in. You had 13 different plugs, sets of plugs. So on any given day, you could just plug them all in and get a completely different combination. Or they could only plug one in, or two, or three. It didn't matter. So what the problem was they would have to figure out how many were plugged in, which links that they were plugged to, and why, and essentially why. Was there any pattern to that? So they were faced with a really serious conundrum. So Enigma wasn't broken in the 1940s by Alan Turing, believe it or not. He broke a version of it. In the movie, those of you who've seen the movie, he discovered that they would say that there were a certain group of messages sent in the morning that were weather patterns, or that they would end every message with Heil Hitler, which led him to believe that we now have a ciphertext and a plain text that we're expecting. So let's put them together, map those letters in our bomb, which he did create the bomb. But if we map those letters already in the bomb, we don't have to go through, all different combinations. We already know that these exist. We already know that these are essentially a combination. So we can cut out an insane number of combinations and just use these specific combinations. So what happened was he was able to essentially predict what they were going to say, set up the bomb using BOMBE to bring in that information, and then when they bring in that information, they were able to break the code in a couple of hours instead of the 25-26, which is what they were doing earlier. Unfortunately, 26. This goes back to the information. Once the information is 26 hours old, it's already happened. They couldn't react to it. So they were basically just a couple of hours away. Well, now they're breaking it in 4 hours. They can react to whatever they want. And so they broke it within a couple of years of the war starting. However, they didn't want the Germans to know that they broke the code, because then they'd change up their system, which is the entire basis of how they broke it. So what they did was they had to essentially do this percentages. It's like, okay, if we react to this, yes, it's going to work, but how much risk are we associating with that? Do they understand that, or are they going to figure out that we intercepted and were able to crack a message? So yeah, he just took advantage of the plain text. He took advantage of what they were supposed to do. So it was actually broken in the 1960s by a major invention that came out in the 1960s. Hint, most of you have one in your pocket or are looking at it right now. It'd be a computer. So what happened was, in the 1960s, computers made the transition from the vacuum tubes to transistors and integrated circuits in the 60s. So what they were able to do was, instead of waiting for the physical pieces to plump down in the bomb, he had to have the physical pieces and the mechanical bits actually flipping. we now did it electronically. So it was basically at the speed of electronics, which basically made brute forcing the Enigma machine, which was still on the physical switches, obsolete because of the technological advances. Essentially, advancing technology wins. It will always win. It will always. If we're when we write cryptography, we only have the current technology in mind. That is why quantum computing is such a big thing in cryptography, because if what happens if quantum computing becomes real, then our cryptography, some of our cryptography aspects and mind things will fall apart because we weren't prepared for it. We weren't thinking of it when we made the crypto system in the first place. So yeah, kind of bouncing ahead a little bit. Cryptography is cool, or history is cool, but how does it really apply to modern day? So that's what I'm going to be doing now, is trying to loop back and apply the same concepts back to the now. So I equate the Caesar cipher. So I have a couple of comparisons up here, and I'll explain why I chose the comparisons that I did. The Caesar cipher is equivalent to 56-bit DES. It was great at the time, but you could pretty easily brute force 56-bit DES within a couple of years after it coming out. I think right now it takes 300 some odd seconds for one of our laptops to break 56-bit DES now. Like it's not. Yes, it was a good concept, but the key space was so small is so small at this point that we can just hack and slash our way through it and have no problems. The Vigenère cipher is I would equate it to the LM hash. The LM hash was a good idea, but the problem that the LM hash had was that it had a specific limit to to the number of characters it could take in, and it would always split the characters into blocks. When it splits it into those blocks, that's when it falls apart and it becomes like the Vigenère cipher, because then you could attack specific blocks. And when you attack those specific blocks, you can break down the hashes. And when you break down the hashes, you can kind of piece it together and finish it off that way. And I would argue the most controversial comparison is Enigma is equivalent to RSA 2048. So Enigma wasn't broken until technology advanced in such a way that caused it to be broken, just like RSA will. RSA, there are ways to attack RSA, but you're not attacking the algorithm necessarily itself, you're attacking the system. It's within. So say I create an RSA key, 2048 key, and I give it to one of you. However, I leave the key on like a Dropbox and leave my laptop open to everybody else, or I leave the Dropbox open to everybody else. I don't encrypt the Dropbox. That's not, the key is, it's kind of moot. I could say that I have RSA 2048 encryption, but the key is readily available to whoever wants to touch it. So it kind of, that's where you want to start, that's where you want to protect it. You don't, like, you know that RSA is secure. Everybody in this room knows RSA with certain key space is secure. However, protecting the keys, you got to protect the keys to the kingdom. Even the public key is something that should be protected, because what's better, giving freely a public key to everybody, or being able to say, you specifically get my public key, nobody else knows it exists. There's no reason to basically announce to the world that you've got an RSA public key. Kind of security through obscurity mentality. So what this next slide is kind of about is kind of stepping into the realm of the 102 and 103 talks that I would be giving as a part of the series. This is kind of like a teaser, if you will. These are the concepts of mathematically broken versus practically broken. Mathematically broken means, to give you an idea, mathematically broken, every encryption out there is mathematically broken. It just is. However, is it practically broken? That's the real question. Because there are ways to brute force different encryptions. There are ways to attack different encryptions. That is the mathematically broken idea. There is a mathematical way to do it. Now, does it take 15, 20 years? Yeah, but there is a mathematical algorithm out there that is a way to attack it. So, to give you an idea, is RSA broken mathematically? The answer is yes. These are the types of attacks that you could perform on RSA keys. Quadratic sieve, Fermat factorization, timing attacks, etc. Like, there are ways to attack RSA. However, it's basically just taking the brute force and then shrinking it down by portions, depending on which method you use. Now, are all of these effective, or will all of these get you what you need? Eventually, yes. But that's jumping into is RSA broken practically? No. The methods above would take years to break RSA encryption. We're not at the technology yet to break it practically. So what it is it's the idea, separating in the mind the idea between mathematically broken and practically broken. So if somebody says, somebody has my RSA key, I know that I have multiple years to change it, but why wait those multiple years? I might as well just change it now. And then at that point, it'll become moot. So if you understand that something is mathematically broken, then you understand that eventually they'll get where they need to go. But the key word being there is eventually. You have time. And depending on the amount of time that you have, you want to give yourself the most time to change the algorithm or to change the key if the algorithm's still safe. So that's kind of the idea behind mathematically and practically broken. So, give you an idea as to some of the resources that I use and am familiar with. These are a couple of titles of books that I've read and used. I'll leave the slide up. I actually have one of the books here with me. It's called Introduction to Cryptography with Coding Theory. It's written by Larry Washington with Wade Trapp. Larry Washington is my professor's professor. So the professor who worked for the NSA, who was my professor, that's his professor. He wrote this book. Kind of like my shameless throwback and shameless plug for him. Yeah, my professor has also written a couple of books on advanced cryptanalysis and algebraic cryptanalysis. In this book, it has the ideas behind quadratic sieve, timing attacks, and Fermat factorization attacks on RSA, and it gives you a mathematical understanding as to how these attacks work and why they work. So what it essentially does is it gives you those ideas and theories. It won't actually show you how to program it, but it'll give you the mathematical foundation for it. That's where most of the cryptography that I've studied comes from, is this mathematical base. It's the root of the algorithm and how it works and why it works. All right, so that is all I have for you. Does anybody have any questions about any of the slides? Cryptography in general, I've I'm open to any and all questions now. I will open the floor to you. Yeah, feel free.
You were talking about the RSA, and I can't remember, is that the symmetric one, or is that the public key?
That's the public key, private key. So to give you a little bit of insight as to how the RSA public key, so Fermat factorization was originally created in the 1700s. What it does is it takes a very large number and then tries to find the primes of that large number. Well, with RSA, there's only two very large primes into one very large number. So if you get one, then you get the other, and then bam, you have the private key, because that's what the private key is. However, it's a little bit more complicated than that.
The effort to do that is impractical.
Yeah, yeah. Well, it's not impractical. It's so. Are you familiar with the RSA challenges that that were around in like mid to late 2000s? So what they did was they basically gave out a public key and said, try to break it. So what a group of mathematicians.
Breaking you mean find the private key.
Yep, find the private key. So what a group of mathematicians did was they actually used Fermat factorization, and so what they were expecting, or what the RSA challenge was expecting, was that it would take multiple years, and they were saying, oh, you get $50,000, $100,000, dollars for these specific sizes of keys. Well, these group of mathematicians, they basically funded their research off of these challenges, because they would break them in about a year, like seven months to a year. So it pretty much, like, yes, it was a very long time, but they had banks of computers at their disposal, and they were able to break it within a year. And they using the properties of Fermat and quadratic sieves, et cetera. There's a couple of papers about like how they did it, because one of the prerequisites was you had to do it and write a paper as to prove how you did it. And they said we used quadratic sieve and Fermat factorization. So about after the fourth or fifth time they did that, they said, okay, we're taking down these challenges, because it's essentially, they used it's a brute force method, but say brute force takes this long, they took about this long. So it's still a reason, it didn't take a small amount of time, but since they had this, they already had the algorithm, all they needed to do was say, all right, let's take in this key. Yeah, absolutely.
So many organizations, or quite a few organizations, have created this quantum computer.
Yes,
Right? So
yes.
the question, when it evolves enough, would it be easier to solve DLP, or CPC DLP problem, break all this?
Yeah, so here's the funny thing. RSA is actually, I don't want to say immune to quantum computing, but it is significantly more protected against quantum computing than most things. RSA is, no?
No.
No?
No. Prime factorization is broken before that algorithm too.
Oh, yes, you are correct. In that case, never mind. I did.
That is like a way, that is like a known problem, DLP, or you see DLP, right?
Yeah,
So
yeah.
Just all about computing power. If you have enough computing
Yeah,
power.
if you have enough computing power, then yes, you will be able to apply these.
So do you know, is it like a case with quantum computing?
Yeah, so in that case, quantum computing, yes, will break modern day encryptions. However, with quantum computing comes new encryptions.
Oh, okay.
It's essentially, so how Enigma was, all right, this is the best encryption that we have. Okay, technology is caught up. All right, now using this new technology, let's create a new encryption. And that's where we got, all of these. So eventually, when quantum computing catches up, it will be like, okay, how can we use quantum computing to create a new set of algorithms with what we have?
So is it only about increasing the size of the key, or is it about creating new algorithms?
So currently, RSA is protected by increasing the size of the key. The reason it is we increase the size of the key is because creating the key is significantly less computing power than breaking the key. So what you would do is once the computing power has reached a certain point, it's like, okay, let's bump up the key. And since it's an exponential function, it's exponentially harder to break the key than it is to create it. So that's kind of the idea.
But what are new algorithms? Do you know any?
New algorithms?
Post-quantum
Yeah.
crypto research that is going into standardization now. Dan Bernstein's leading a lot of it about creating new basically quantum resistant algorithms, because RSA, ECDH, all these algorithms.
AES
are
as well.
broken. Well, AES, there's Grover's algorithm for symmetric things, and AES 256 is still fine, but lower values like AES 128, you have the security. So it'd be only 64-bit security, which is not sufficient. So post-quantum, they're looking at new algorithms that you can compute on classical computers that are resistant once quantum computers become real. So they're looking at things like DOPA codes, which is like in error correction stuff. They're looking at a lot of lattice-based stuff. He's done a couple, if you look at the chaos communication counters, their videos from either the year before, last year, or the year before, he did a really good talk on what are we going to do about quantum computers.
Yeah. Yeah. No, I haven't gone too deep into the quantum computing realm. Most of my stuff is kind of like the history and like advances throughout history. But eventually, I'd like to reach the point going in. Yeah, yeah, pretty much. Learning about the history allows you to understand why it was broken in the past, and allows you to understand the method, if there's any methods today that we can, yes, we've got this crazy new key or this crazy new algorithm. However, if it's entirely dependent on this specific one thing, and this specific thing is really easy to break, then it becomes a moot point. Are there any other questions at all? Thank you very much for coming. I appreciate everything. And hopefully you have a good rest of the conference.